so what I thought today, like maybe we can, like I reckon, ask questions of stuff we've dealt with. I know last week we, or on Wednesday, we did like this food pizza thing, and around ADTs, and I think I think you guys have probably got it. It's pretty simple. It deals with this like sum type. It's the ability to create a sum type, something which is like one or the other, right? Which is pretty handy. And the cool thing about it is it's really simple actually to understand here. When this kind of idea is wrapped up in classes, because you can obviously do this in OO as well through like abstract base classes and then concrete classes, but often it's not quite as visible as this. Like you certainly can't, in sort of 23 lines of code see this kind of relationship between classes. Do you know what I mean? There's a lot of boilerplate that's going to hide the structure. You're never going to see it as simply as this, which I really appreciate. Like this for me is brilliant because I can totally see how, like I can see that food is what did I do? That food is like, oh, it's a pizza or a pasta, and a pizza has a base, and a base is a normal, a gluten-free, and a topping is a thing. And it's like, this is brilliant. Like I can see that structure really easily. When that's wrapped up in classes and abstract-based classes, it's quite hard to see that, because it's never going to be as simple as that. Like those 3 lines to show you what toppings are. Of course, they're very different, but I mean, you can think about the way you would model data using classes. Classes obviously also encapsulate behavior and stuff against those things, which obviously we don't have inside this. This is just a representation of data. There's no methods or functions on that data wrapped into it. So there's that separation. Okay, so the one thing I thought, because I'm going to trash this whole thing. Oh yeah, so just as a reminder, then we moved into a quick overview of like what are type classes, which are like actually very simple. It's kind of the concept of interfaces onto data types, and those could be any data types. It could be your own data types, and of course those data types are, could be ADTs as well, or like these kind of optional. I mean, the sort of like sum types, right? So. And I think this kind of makes sense. Like the type classes are pretty easy to understand. What's quite tricky is like how to model stuff using them. But I feel like when you practically write code, that's where I sort of played with type classes, where it was like, okay, I've designed, like I've modeled out, my problem or whatever in terms of data, and it's like, oh, I need to print it now. Like I want to print this thing. It's like, okay, so how do I do that? I expect to find a function called show. Show is the like global function for turning anything into a string. And then it's like, okay, the compiler will tell me that, I haven't done it. I haven't implemented that type class. If I take that out, it goes, hey, like you haven't implemented the type class show for food. And then it's like, okay, yeah, so let me go do that. That totally makes sense. Implement the type class, and then that's fixed. Over here, it was like, oh, I was comparing them to each other. So if I didn't have the EQ type class, that would be a compiler error. So it's like, just write code. The compiler says, hey, you need to implement this type class. Go and implement that type class, right? And that's kind of how you work. This is how I work through these things. It's like I go, oh, yes, of course I need to check these things for equality. So let's write the code that does that. Compiler says, hey, go and write me a type class for EQ, please. And then you go, yeah, write the type class for EQ. That's kind of my workflow through these things. Like use the compiler to guide you through your problem, and that works for me. I mean, as opposed to saying, hey, like, designing like the canonical food object and saying, well, foods can be shown and equality and maybe they have ordering, and like figuring out all the hundreds of different type classes they could follow. Rather just implement the ones that you need, as you go through your problem, which I think makes sense, right? So is there any questions on any of these things? That stuff makes sense?
I have one small one.
Yeah.
If you scroll down to where the equality one is defined,
EQ food, yeah.
The instance show base or instance EQ food, like,
yes.
Are those names used anywhere? Like, is there a purpose to those names?
I don't think so. I'm not sure why you have to name this thing. You certainly don't have to do this in Haskell, I don't think. So I don't remember ever having to name these things. I think this might be the fact that, it compiles down to JavaScript. And so PureScript wants to give this thing because, if you
Object
think
name.
about it, this probably does end up becoming some kind of JavaScript thing. And it probably wants to give it a nice name so that when you go and look at the JavaScript that's generated, that you see that name appearing. Do you know what I mean?
All right.
But I don't
Yeah,
think
that
in
makes sense.
Haskell you have to do that. Yeah. So that is a bit odd. Like this name is kind of meaningless. It's meaningless in the context of PureScript. Like that name, I don't think even, I don't think it has a meaning at all. But you still do it, and I see it being done everywhere. I don't think in Haskell instance example or something. Let's see if we can find one. I don't think in Haskell you need to give it a name. Instance. Come on, give us an example. Yeah, there we go. So here's the implementation. Is that so? Oof. We have to think about in Haskell now. So Haskell's not quite exactly the same as PureScript. It could be more hairy. Instance EQE. That doesn't seem weird. Oh, okay. Oh, wait. Oh, I see. So collects. So it's like, you can see there's no name being specified, but like, I don't understand this completely, but it almost looks to me it's like the instance of the collects type class of E, where E is constrained, has already got an EQ type class. So it's like, if you think, so it's, if that kind of makes sense, so it could be like between EQ and show, it doesn't really make sense. But maybe when you've got ordering and you've got EQ as two type classes, you could say, hey, ordering needs like it also relies on the fact that there's already an EQ type class for that thing as well. And so that's what this is saying, I think. This is saying it's the instance of the type class collects of type E, where E already has the EQ type class implemented for it, if that makes sense. So you can see that these things, I mean, this is like some of the like crazy power that you can do is like, oh, look, I mean, you could think of it as like a derive, it's like it's like a type class deriving from another type class. So it's like collects derives from EQ in some sense. You know what I mean?
Yeah, that makes sense.
Yeah, but you can see, you don't need to name them in Haskell. There's no name : thingy there. So they're similar, but probably not the same. I don't think we should dive down this craziness.
It was just a small
That's
question.
like, yeah. There's like this kind of stuff is like, this is where it just becomes so broad. There's so many ways of like doing stuff, but like you start to recognize common patterns in the language where you go, oh, the fat arrow, it kind of tells you that E. So the fat arrow, although it looks like it's like maybe it goes from EQ to a collects, the fat arrow is more a constraint. EQ is a constraint on E. So collects of E, where E has an EQ thing. So it's the same in our little functional thing here. If we wanted to go F and we take a anything to an anything or whatever, so it's like for all A, anything to anything, right? You can say where A has an EQ type class. You know what I mean? And you can have many of them. So you can say where EQ A is the type class EQ, but it also has ORD, and it can flow like that. So it's like then we know when we're dealing with A, we can go, because we don't know what A is. A could be an int or a string or a char or a food or whatever, right? It's of any type. But we know certainly that we can call EQ on it because we know for a fact that it has an EQ type class associated with it. Do you know what I mean? So it's like, and often like you don't design these things up front. You go, okay, so like I'm writing a cool function that like maybe it's, I don't know what this function is, but it's like, say it's just like checking two things are equal, right? Which seems a bit dumb because we already have that. But so we know that, no, so yeah, because well, it's not checking that they're equal because it's not returning a Boolean or something. So it's going from an A to an A. It's the identity function, right? I don't know. But like this is a bad example. But say we know that we're going to in our implementation, we're going to need to check equality of A somehow, then it's like, as soon as I save this thing, it's going to say, it's not, because it's weird. Like EQ is expecting another piece or whatever. But we know we're calling EQ on that like generic type variable A. The compiler is not going to know which EQ to call. So we have to tell it, well, A must have the type class EQ associated with it. Then we can call EQ on it. The same is true of show. So if we were going to call show and we were going to convert this thing into a string, we would, and we're also using equality potentially, then it's like, oh, brilliant, we need to have show for A also available. So it's kind of, it's like more powerful than interfaces, that's for sure. It's like a functional version of interfaces, if that makes sense. So it's like, I want to call a function, as long as there is one somewhere, as long as I can call show on this type, I'm happy that it's of any type. You know what I mean? It's a bit odd, I suppose. Maybe you consider it a bit odd. It's more of like a practicey thing, I think. Any other questions on this stuff? Nope. Okay, I'm going to delete it. So the one thing so I actually thought this morning, like, what would be quite cool is to dive into, like, maybe just touch effects a little bit. That should all compile. Yeah. But what I realized is we have missed something quite important around functional languages, and that is composition. Like, we haven't dealt with functional composition at all. And I'm not sure if you guys know what composition means. Does anyone want to take a crack at it? Just in general, what does composition mean? If I compose things, what does that mean? This is for a Kit Kat, by the way. Anyone who answers this gets a Kit Kat. Even if it's the wrong answer, you get a Kit Kat.
Okay, I'll go. So I'm assuming it's like just the creation of, like, I'm thinking of like orchestration in like a DevOpsy type way. So maybe composition is the similar idea of like creating something from like little tiny pieces, something like that.
Yeah. That's a Kit Kat. Yeah. Any other attempts?
So I suppose it's you can maybe have two. The way I'm thinking about it is two types of composition. You can compose an object from two different, like, I suppose two other objects, like two other definitions or structures, and then compose them into one structure, or like two functions. I suppose I'm thinking of like you pipe the result or forward the result from one function to another. I suppose that's composition.
Yes. Okay. Yeah. So like you're both on the right track. Drickus used the word like orchestration. So that kind of, when you talk about orchestration, I think about like ordering. Like, order makes sense, right? Like, do this, then do that, right? That's what orchestration means in my world. And composition maybe speaks to that. And then Terence, is your answer when I heard it is like you're kind of bringing two things to get like two disparate things into like one thing, right? And that's also like along the right direction as well. So it's actually so stupidly simple, Oaks. Like, composition is like, it's very simple. It's like, if I've got a function that goes from A to B, so like given an A, it will give me a B, right? And this is not it's not compilable code, but just imagine this. And I've got another function, G, which goes from a B to a C. Then I can compose, then it's like E, F, G, H, right? Then H, and so composition is saying, okay, so composition is saying, if I have these two functions, F and G, then I can compose the function H, which using those two will take me from an A to a C. So the composition of F and G will be the function H, which goes from A to C. This is like the mathematical composition example. So if you imagine I've got a function which takes something from an int to a string, and then I've got a function which takes a string to a double, then I can imagine a world where there's a function which takes an int to a double, because all it does is it calls the first function and then the second function. So the composition of the first function and the second function is a function that goes from an int to a double. Do you know what I mean? That's what composition means. So there is an implied ordering here that it's like, oh, F and then G will go from A to C. And then also Terence's thing of saying, oh, putting these two things together will give me this. So so it's like, when here's the implementation. So let's actually do it like with ints and strings and stuff. I think that make it more concrete, right? So what do we want to do? We want to go, like, let's just work with strings initially. Let's just do that. So we'll go like, let's just like implement the toUpper function or something, right? This goes from a string to a string, and it's going to uppercase stuff. And actually, I'm going to use the uppercase. How do we do this? There's probably like a toUpper function, I'm hoping. I'm just going to steal their function. Yes, look, toUpper from the data.string.common library thing. We're going to import that toUpper. And so my implementation of toUpper and I'll do this like dumb first. So I take an input and I call toUpper on that input, right? And it's like, oh, there toUpper. Oh, do I have to import? Do I have to build this maybe?
I think there's no underscore.
Oh, sorry. Yeah. Oh, yeah, 100%. Thanks, Bhavesh. toUpper. Sorry, yeah, it's spelled like that, right? Still giving me an issue. Do I have to import this module? Oh, unbelievable. PureScript strings. This is our first use of the string library? Must be. Yeah, okay. There we go. Sorry, we had to import the package. And now it is saying, what's my issue here? Am I in the wrong project? Learn, yeah. Import of data, yeah, okay, there's some redundant. Oh, it did succeed, sorry. No, it has succeeded. It's just that I've got these redundant imports up here. That's fine, let's actually whack them. Yeah, we can always re-import these. Okay, sorry, there we go. Okay, so I've made my own toUpper. Don't be confused by that. Imagine this is just ... right? It does string uppering. Of course, we can, like, if we were clever functional people, we could go, oh yeah, like this input thing is redundant, right? Input there and input there. So technically I could kill it there, and like, oh, look, that's actually a simple implementation. My toUpper is the same as that one's toUpper, which is already a string to a string. But I'll not confuse things and do it like that. Okay, so we've got a function that does toUpper, and then like append foo or something, right? Is we'll make another function which is a string to a string, and append foo takes input and it appends foo to the back of it, right? Comfortable with those two functions, guys? Yeah, makes sense, right? So this means I can do something like, let's make a little let expression here, let in. So we'll say my string equals, and then the first thing we're going to do is we're going to take, okay, I'll write out I'll say Tom's string is my string, and then I'm going to go, actually let's just do it in here. So we're going to toUpper that first, and then we're going to append foo to that second, right? I'm using that. Everyone remember when that does? And then we're going to log this string, right? So remember the dollar just effectively means bracket that stuff. Yeah. So we can see that there's a natural ordering, that first it's going to run toUpper on Tom's string, and then it's going to append foo to whatever that was, right? So if we run this now, we should see, okay, cool. So that, like, it totally makes sense, right? It uppered the first part and then it appended foo after it. So there's certainly like an ordering happened. If we change that around and we say toUpper of that, it's still cool, but now we're going to see the foo also gets uppered because that happened first. So it appended first and then it uppered, right? Okay, comfortable. So we've got two cool functions that, if we think about it, are composable in some sense. So we could have said like, let's just make another cool function called do both, which is a string to a string. And we can say, oh, do both takes a string and it calls, it does this. It does to upper, then append foo of that input. And now we can call do both down here. You agree with that? And effectively what we've ended up doing here is we've said, yes, we've composed these things. We've composed that function and that function. We've composed them into do both. Yeah? Happy with that. But really we've like practically composed them. We haven't really used functional composition to do it though, because we haven't really joined the functions together. We haven't really done that. So there's and to make it maybe like more concrete is there is I think an operator called this. Yes, called compose. Oh, sorry, it should actually be, it's this one, because of course the direction of things is important. So compose. So check this out. Ignore that. I mean, you could understand the type class, I suppose. There's a semi-group OID, and there's a function implemented for it where compose looks like this. Actually, we don't even need to do that. So, and like, let's try and understand this. So compose is a function which takes 3 parameters, right? A function, and a something, where, and look what it's going to do. It's going to call g of x first, and then it's going to call f on the result of gf of x. And if you look at like what we did here, if we actually put our brackets in, it's like, oh, look, we've got the same kind of pattern happening here, except what happened is we only took the one parameter x. We just implied to upper and append foo. We've embedded into our very specific function. So what composes here is it's like a it's a more abstract version of our do both, where they just said, oh, actually this to upper part, we can call that G, and this append foo part, we could call that F, right? And so we can call, sorry, is that the right way around? Yes. Call that G, and we call that F, meaning that like, oh, you could pass, so now we've got more parameters that need to be passed in. And it's like, well, what are they? It's like, oh, it's any function which takes a string to a string. And this one is any function that takes a string to a string. And now it's like, oh, do both. So it's like, I can now say do both. The first one is to upper. This is like, we're going a bit mad here, but it's like, see where it goes. And so my do both now takes 2 functions, a to upper and append foo on that type. And effectively what we've ended up rewriting is something called compose. Does that make any sense? Like, oh, look, we made them the same. FG input, FG input, FGX. Does that make sense? And then what we can do with so their version of compose is like much more cool, because it's like, oh, it doesn't have to be string to string and string to string. It could be A to B and B to C. Given an A, give me a C. Which was like, oh yes, remember our cool ideas. Like if you've got a function that will go from an A to a B, oopsie, and another function which goes from a B to a C, then there must be a function that goes from A to C. It is possible to describe a function which goes from A to C, because obviously it just invokes that, then it invokes that. And it's like, oh, we've just done it. So like we've written a function which does exactly that. Given a function that goes from A to B and a function that goes from B to C, give me back a function which goes from A to C. And here's the implementation.
Just a question, sorry. Yeah. So I'm assuming it's inferring the type of C, and then that's what's going to be returned.
Yes.
I'm just trying to think, like, if there's an a return type, a data type that's not part of your inputs? Like how would you do that? So would you just specify the type as the end?
No, you're quite right. So composition will only work where, so if you look at this description, remember that it's like this B must be the same as that B. They must be equivalent. And that C must be the same as that C. A must be the same as that A. You cannot break that rule. So you can't have a function that goes from an A to a D and then a function that goes from a B to a C. Like they don't compose. They just don't mathematically compose because there's no. Does that make sense? Like the constraint is like they must be, like that A there must be the same as that A there, and that C there must be the same as that C there. There's no other way. So like if you're saying, oh, but this needs to be a D, it's like, oh, well, it can't be done. It's like, well, then how the hell would I do that? I can't do it. It's like it doesn't. There's no maths solution to that problem. Do you know what I mean? So if like your question is like it's not possible, then you wouldn't be able to compose things together to make that happen. You wouldn't be able to. I think that's what you're asking. So you're saying like if you had a function that went from a string to a string, then a string to a like an int or something, can I compose this one with this one? And the answer is like no, because that int doesn't match string. Can't be composed. But they could be composed where the types change in between. It's like as long as the one that you're composing, like as long as G takes as its first parameter whatever F returns, then they compose. Do you know what I mean? So like, because I can go from A to B to C, like that's okay with these two functions, because here's the first function and there's the second function. Like that's okay. And I could therefore also go to D if I had another function which took me from C to D. Like, but they have to chain. You know what I mean? Then I can compose these three to produce a function that goes from A to D, because it just kind of skips those steps, and it doesn't skip them. It can hide them away from me. It can abstract them out. Do you know what I mean? I mean, like this is a bit theoretical, I guess, but it's like what this allows. I mean, it's obvious that we can do this, right? You can do this in any language. Like if you've got a toString and a toUpper, and they strings and strings, I can call the one and then call the other, and I could turn that into a new function, right? Called string and then upper or something, right? I can do that in any other language. That's fine. What a good functional language will do is it will make that really simple. And so here is how you can make it really simple, is by making use of their compose like higher order function. This is like this is a function that can apply to stuff that it doesn't care about. Like it doesn't care what the types are, as long as they kind of match, as long as F and G and X match each other down there, doesn't care what they are. It doesn't care if they're int, strings, lists, maybes, whatever, doesn't matter. You can compose them. And the awesome way that the kind of like how simple it can be is that do both is like toUpper composed with append foo. Like that's it. So that's the composition operator, which says do. So I'm trying to remember the ordering here. It would be this one first. So this is like the reverse version. Do that one first. So append the foo, then call the toUpper, giving me back a function. So check at this. Here's the interesting part, is like do both is now a function. And if you look at that signature, it's almost exactly like what we had. It is a function that is the composition of those two things. Does that actually, I don't think that actually is the right signature. It should just be a string to a string. Well, let's try it. Yeah, it is just a string to a string. Our compiler is being dumb there. Oh, sorry. Let's kill that stuff. That's probably why it was giving us issues. Yeah, no type declaration was. So do both is a function which goes from string to string. Like simple as that. And we're using the composition operator there. Is this mind bending? And look here, look, we're not like creating a new function that like takes a parameter and then passes it around to these things. We're just saying to the language, like, hey, just compose these two things together. Like, you know that append foo is going to give us a string, and that the first parameter to upper is a string. So then just compose them together, giving us a new function which takes that string and returns that string. Like, join them together. So whatever I pass in to do both will execute append foo first and then to upper next. And we can obviously write it the other way around, which is, in my opinion, easier to read. Append foo that way to upper. So it will be that one first and then that one next. Weird, not weird, comfortable, not comfortable.
Yeah, for me, this actually makes a lot of sense. And it's from like you said at the beginning, the different approaches for different people. So starting from the theoretical g of x and then f of x as g of x as a parameter, like that makes a lot of sense for me.
Yeah. Cool. So this is quite it's fairly important, because you'll see this a lot in functional, and they quite often call this, so in Haskell this is dot. There's an operator called dot, where it would be like h equals g after f. That's how it would be written in Haskell, with the dot, not this arrowy thing. I like personally prefer this, because it's like, this is clear to me. This dot thing is batty, and also the dot isn't like reversible. It's not like a it's not an operator that like what's the opposite of like the reversed version of dot? Like, I don't know. It's not clear to me. Whereas I know what the reverse version of this is. It's like, oh, it's arrows the other way, right? Which is pretty cool. But and the way in Haskell certainly is like, the way this is described is they would call this G after F. So H is G. They call that like operator, like maybe they call it the operator. It's the composition operator, but you would say it in English, G after F. G after F. That makes sense? And it's like, this is just a simplification of like H taking a parameter, which is equal to G of F of that parameter. I mean, these are like, they're equivalent. It's just, you can simplify it by saying, oh, just compose the functions here. Don't care about, like, don't pass the parameter into it. Just join them together, giving us a new function H, which we can then go H of 5. You know what I mean? They're functionally equivalent. And we saw that. We could see, because compose actually is implemented as that. F. It takes the X, calls G on that X, and then calls F on that, on the result of those two things. It's a bit wacky, but like, you'll get used to it. So it's like, either you build a function that takes all of its parameters and then calls those functions with those parameters, or you compose the functions together, and later on someone will call it with the parameter. Like, they're equivalent. You could write them both the same, and there's no real difference from a runtime perspective between these two things. Not really. It's just like, maybe that looks a bit different. Okay, so we're happy with functional composition. Yes, go. Sorry, Terence.
Wait, another stupid question. If I wanted to call append foo like more than once, like for, let's say, X number of times, would I just then add another like composition arrow and then just add it? Or like, say I wanted to do it and I'm not sure how many times I need to append foo.
I see what you're saying.
That's just a simple loop, I guess. Or is there something fancier, I guess, to do that?
There's never anything as simple as a simple loop, unfortunately. So like, a simple loop implies recursion, which is not simple. But like, if you wanted to call, so in your composition, you could of course put this, more than once. That's fine. So like, it will call append foo, then to upper it. And we've used composition to describe that, which is fine. But if you wanted to do that many, like you wanted a function which is like let's just call it like do something, and it was like, okay, so what we want is we want to call we want to call append foo a number of times, right? So it would be like, well, how many times, and then you want to return a string, right? Something like that. Yeah, so I suppose we could go append foo many, right? So let's create a function called append foo many. And yeah, okay, so it takes an int, so a number of times. Let's call it like count, maybe, that thing. And now it's going to call append foo this many times, right? Oh yeah, and we need an input, right? Of course, yeah, sorry, we need an input. So that's our input, and on input, and it's going to return us a string. So let's see how we would actually implement this. I think we might use some composition here, but like, what would be a strategy of doing this? Does anyone have an idea of how we could call append foo many times? I think the answer is recursion. Does anyone have a guess? Yeah.
I was thinking it would be similar to how we did like you said, the recursion example previously. We would have maybe an override that accepts the one count and does just the simple logic versus the many count, or the default that will just call itself X time until it reaches the one count one, and that will end case and finish off type of thing.
Yes, brilliant. Okay, yeah. So that's good. You're thinking about the terminal case. So you're saying actually we count as 0, right? And you get an input. The answer is what?
The input. Yeah.
It's just input, right? Yeah. So if someone says, hey, can you append foo 0 times to this input? The answer is it's just the input, right? And you probably could say, well, what if he gives you a negative number? Like, that's fine. It will blow up. That's probably where a guard would come in. Like you would almost say like append foo. So well, let's get there. So, and then, okay, so alternatively, if it isn't 0, what do we want to do? We want to say, what, Miguel? Have you got the solution to this one?
So, I think you'd call the original append foo and then pass the result of that in to append foo many with count -1.
Cool.
That makes sense.
Yeah. So we're gonna go
until you get to your terminal case.
Count -1 with input appended with foo. Oh yeah, we can call append foo, right? The earlier one with append foo of the input. Does that make sense?
Yeah, that's the way I was thinking. Probably very naive approach, but yeah.
No, I think that's exactly perfect. So I think that's exactly what you were. This is exactly what you wanted, right, Terence? Append foo many means we can append foo many 5 to Tom's string, and now we can hopefully get foo appended 5 times. Check how brilliant. You will have to get over the solving things with recursion, because there's no other way. There's because we can't append foo and then do it more than once. It's like there is no variable we can append foo to. So you have your variable has to be on the stack, actually, if you think about it. There's maybe just a slightly cleaner way of writing this whole thingy. And here's maybe how, and I would say use guards. So I'll just make an append f function, and just to see guards in action, append f. And now with the guard, we would go, so we go count and input, and then effectively you just put this little thingy here, and you say count less than or equal to 0 equals input. Otherwise, append foo many, that thing with append f there. So there's does that work? Why are we getting issues here?
Do you need an equal sign?
Oh, sorry, yes. Otherwise equals. Yeah. So that's, thanks, Pravesh. That was it. So append f these two functions, I mean, they're going to be identical from a use case, and probably even from a compilation, like from a runtime perspective, they're functionally identical. But here you can see how the guard is maybe neater, because you're not like repeating the name of the function so many times. You're saying appendf takes out two things. Here's the one scenario. That's our terminal scenario. And the cool thing is I was able to go less than or equal to here, whereas I couldn't go here. That's only going to pattern match in equals. It's not going to pattern match the less than or equals. So this is maybe a superior version of this, because you could blow this function up by going, and this could be dangerous, like -1. I don't know what it's going to do. Could not, oh, sorry, append foo many, yeah, -1. Why is it not happy? T is an unknown type. It could be that we are lucky that ints are unsigned. Yeah, we are lucky. So ints are unsigned. Okay, so they can't be negative. So that's a win. So that's fine. Actually, you're safe. I think you're safe.
I have a question.
Yeah.
In Haskell, when I played with it for like 2 weeks or something, I remember that when you specify negative numbers, you have to bracket them, I think. Is that maybe what the problem is? I don't know what it's called in the language, but...
Oh, no, you're right. Yeah, perfect. Oh, yes, good one. Yeah, it's because probably minus is like an operator.
Yeah.
It's an operator, yeah. So like by putting it there, it's like it gets confused, because like minus now is taking 2 parameters or something. That's probably how the parser is working. Yeah, quite right. So this is going to blow up, isn't it? Should we run it?
I'd like to see what happens.
Look, nothing happens. It doesn't exit. Hello, no answer. So it's like it went down a death loop. Whereas hopefully in this version, it won't go down a death loop. Yeah. Yay. So, okay, so guards are better. I mean, they're not better, but they can be more powerful, because you could go like, hey, count is less than 0, and, I don't know, count is, not, what was I not equal? Not equals 5 or something. Then it's the input. Do you know what I mean? So you can have a more powerful thing there, whereas the pattern match is only on equality. You can't do like a cool kind of like predicate. I think you call this a predicate up there. Okay, comfortable with guards? So guards are pretty weird, because it's like, when I think about the syntax of guards, I go like, oh, but I'm expecting an equals up here because I'm defining a function, right? And I'm expecting an equals. So but there isn't. It's like the guard starts as part of almost like the function signature, and it specifies its own equals. And then there's like another guard after that one, which specifies its own equals. So like syntactically, it's strange to parse these things as a human. But that's the syntax. And you'd almost expect it to be like, if this was any other language, I'd expect that to be an equals, and then like this to maybe be an arrow. I don't know. And then I go, oh, okay, yeah, it's a function. And then, oh, it's like a case statement starts here. And it's like, okay, and there's 2 different branches to it. But it's like, no, actually it starts before the function is equals. And now the function has 2 equalses. It's a bit weird. It is weird. It takes a bit of getting used to. But it reads easily. I mean, if you just look at it and the compiler tells you that it compiles, it's like, yeah, okay, got it. Simple. That equals, though, yeah, can be a little bit tricky, as Bhavesh pointed out earlier, that I left it out earlier. Okay. Happy with the appendf. So let's just like touch effects for 5 minutes before we all run away to our weekends. Let's just like look at them very briefly. So it's like effect. So remember, this is valid, right? Is we can go, oh, sorry, log hello world or something. Yeah, let's kill that. And like, so here's some here's some constraint on PureScript Haskell, is we know that these are pure languages, so they can't generate side effects. So a log, like logging a string to the console, is a side effect. Can't be done. That cannot be done, except it can. So, and only in one place can this be done, is as the return. It's kind of like I take my effects and I wrap them up into objects. So I can talk about the ability to log a string to a console. This line of code, though, is not going to go and do this. It's not going to, at this point in time, log this message to the console right here. Really what log is you can kind of look at its signature. It says like it takes a string and it gives you back an effect of type unit, right? It returns an effect of unit. We don't know what unit is yet, but unit is a function that effectively returns nothing. It's kind of like you get kind of two interesting types, I suppose. Certainly in PureScript Haskell, you get a type called void, which is an unconstructable type. So void means you can't construct this thing. There's no element of type void. So void is a type. So remember, if we talk about like int as a type, it may have, and I don't know what the notation for an element is, but like int has got a whole bunch of elements. It's got like 1, 2, 3, 4, 5, up to, you know, like whatever, a whole bunch, up to max int, right? These are the elements. These are some of the elements of type int. Comfortable with that, right? It's like you could also think of string. String is also like, this is almost like thinking of them as like sets, right? So the set of type string has got like all the possible strings you could ever imagine inside them, right? And it's like quite clearly you recognize there's like an infinite number of them, right? You could do the same thing with like list of type int. Could be like in the like some example elements of the type list of type int could be like the list of nothing, of no ints. But it could also be the list of like 1 onto empty, or it could be the list of 1 and 2, etc. Right? Dot dot dot. Many. Also an infinitely large set of possible elements inside that type. Yeah, you comfortable with that? Like just example elements that you might find inside, and like you kind of it is quite useful sometimes to think of the PureScript or Haskell type system in terms of sets. It is actually a good analogy. So does that make sense? So the int type has a whole bunch of potential elements that it could be. The string type has got a whole bunch of potential elements that it could be. Sometimes infinite, like the string one, and sometimes not sometimes bounded, like for int. Int only has like a set number of possible values, something in the 4 billion range, right? But we know that we can't have more than min int and max int, right? List of int is exactly the same. This is more on the infinite side because you can have an infinite number of lists of ints, different combinations of them, right? So void is also a type, but it has, so what elements does it have? It has none. Like you can't, there is no element of type void. There is no element. There is another type called unit, and unit only has one element in it. So you could imagine that unit only has one element, like let's give it a name, call it Bob. Bob is its name. Does that make sense? So the unit type only has one possible element. Void has absolutely none. So this almost tells you can't construct an element of type void because you like, which element would you pick? There are no elements to pick from. So there is no such thing. So you could talk about the type, but you couldn't ever concretely generate an element of that type. Does that make sense? Whereas unit is kind of similar, where it's like, okay, I can talk about the unit as a type, but I can also construct one of its elements. There is only one, and it's called Bob. Actually, it's called unit, I think. That's it. Does that make sense? So it's like there is only one type. So this means, oh, that's cool. So like it's actually quite batty when you think about stuff like this, because I know we see the word void in other languages, and that means like returning nothing. From a functional perspective, it's not really possible. You can't return nothing. There's no such mathsy ability to do that. And so a function which takes a string and returns a thing of type void, like you cannot write this function because, well, return me a void, please. It's like it's unwritable. Does that make sense? Like you can never write a function which returns. Like this is actually I think in Haskell they call this absurd. This is an absurd function because it cannot. And so quite commonly like a function that always does or like always returns the same. It's almost like it wants to throw away the element given to it. Is like, oh, that must return a unit because we can return an element of type unit, which is called unit. So unit is possibly more similar to what you've previously seen as the word void in other languages. Void not being the thing that you that you think it is in Haskell. Really, what void means is like it's an absurd scenario. And however, it does have uses because it can be used as a constraint. Yeah, it's a bit of theory, but does it kind of make sense to you though? Describing it in terms of like sets like this.
Yeah, makes sense.
Sort of makes sense. Okay, so when we go and look at effect down here, we can see. Oh yeah, so sorry, we were looking at log. So log is a function which takes a string and returns an effect of type unit. So that effectively means it's like it's an object called effect, like a type, which really doesn't, you know, which describes like of no. It's almost like an old school void type. So it's just like an effect with nothing inside it. An effect of a useless kind of unit attached to it. It's like saying we could have a list of type unit. L is of type list unit, and it's like, well, that's really kind of useless because like a list of units is pretty, you know, it's like kind of meaningless. It's like it's discarding the. Maybe that's not the best example. Effectively, but like what you this is actually a good example. Like f is a function which takes a string, returns us of type unit. When you look at it, effectively it does, like you kind of know it does nothing with the string. It can't do anything with the string. There's no way of like returning anything other than this unit type, which has no meaning. It's a meaningless type. It's like given any old string, I'll always give you back the same element. It's like, oh, I'm discarding the string then, effectively what that means. I'm like throwing it away. And you can see it here. Unit is not used on the right side. So maybe that's, I know we're at 9 o'clock now, and unit and effects I think require almost a full hour. But there's maybe some prep around the types void and unit for you guys to mull over the weekend. Any other questions, guys, before I press leave?
Happy from my side. Thanks, Tom.
Cool.
Yep, all good. from my
Vivesh,
side.
Terence, Matt.
Thanks,
Yeah.
Tom. This one was
Yeah,
cool.
fine.
Cool.
Awesome.
Awesome, guys. Have a great Friday and a good weekend.
Cool.
Thanks, Tom.
Cheers, everyone.
Cheers, everyone.
Cheers,
Bye.
guys.
Cheers, guys.